inward radial flow reaction turbine. So under that reaction turbine, we will previously already discuss what is reaction turbine. If the inlet of your turbine, the energy, pressure energy and kinetic energy is available, then that is called as reaction turbine. So here is study inward radial flow type reaction turbine. So this is your study of velocity diagram of inward radial flow reaction turbine. This is your velocity diagram, inward radial flow reaction turbine. So this is your radial shape is there. If you are considering a point of O, that origin, that is your R1 for inner radius and R2 for your outer radius. And this is your VF1, which is called as flow velocity. And this is your V1, that is the inlet velocity of your jet. And this is your VR1, what is called as relative velocity. So using of U1 and V1, there is a VR1 velocity, that is called relative velocity. And UN is also called as blade velocity. And BW1 is your wheel velocity. So according to angle of V1 and U1, the angle is called as alpha, also is called as blade angle. And according to your relative velocity with your BW1, that is your theta, that is also called as vane angle at inlet. Similarly, here is also there, that is your U2, VR2, V2, VF2, BW2. Like similar, U2 is your blade velocity of outlet, VR2 relative velocity of outlet, V2 is your outlet velocity of blade, and this is your VF2 flow velocity of blade, and BW2 is your wheel velocity of blade at outlet. Similarly, there is angle occur in a phi and beta. The phi angle occur is a U2 and VR2, which is called as outlet vane angle. And using this velocity V2, the angle beta is occur, that is also called as outlet blade angle. So this is the main things that given in your velocity diagram. So this is also called as angular velocity diagram. So using this angular velocity diagram, we discuss the efficiency and find the efficiency of a inward radial flow reaction turbine. The necessity for efficiency, we have to find the work done. So going through this work done, first we will find the what are the force acting on it and what amount of water will be go through the turbine. So first of all, we discuss mass of water striking per second. The mass of water striking means what? When the water will flow through the penstock, it goes through the nozzle, and after getting nozzle, it goes through the casing section. So the how much amount of water will be strike, that is called as mass of water. That is represented by rho A V1. So how it will get rho A V1? Because mass is equal to m, we represent the density. That's why we can write mass is equal to density into volume. So mass is a density into volume. Using this density, using a mass of water striking per second, means mass per second is uses. So using this density and volume, we can find it into rho A V1, whereas A is the area of the jet and V1 is the inlet velocity and density is the water density. That is the similar given, that is called as mass of water striking per second, that is rho A V1. Then after we also consider what? When you are striking there, the blade will be take some movement. So using this movement, we can find the momentum from this striking of vane. So that is a momentum of water striking on the vane. What is the momentum? So when mass of water will be strike and that takes some moment of vane, that is your velocity. When the water will be strike on your blade, the blade should be moved. How much amount of move that should be here with respect to time, that is called as velocity, that is taken rho A V1 VW1, which is tangential flow time. Here is considering this is a tangential flow time because if you considering mass into perpendicular distance, this is a V1 is here, some angle alpha is there. That's why we can consider this angular perpendicular velocity. So what is perpendicular velocity means tangential flow velocity, which is come from V1. So V1 will be across through the VW1 is a tangential type. This is a velocity of wheel of tangential type direction is there. So using of V1, you can write V1 cos alpha is equal to VW1, which is called a tangential flow because we representing in a horizontal vertical axis when you represent something. So if you consider horizontal vertical, they represent 0 to 180 or 90 to 270. So in this way you can represent this. That's why we take considering your tangential type velocity. That's why momentum of water striking the vane is equal to mass into tangential component velocity, which is your VW1 from this figure. Next one is your this is the inlet section. Similarly, outlet section considering momentum, that is your mass into similarly same thing. Tangential velocity of outlet. So here is your V2 is your tangential velocity and this is your beta is your triangle. Considering this triangle, consider the name given A BC. So using this triangle ABC, you will find the VW2 is the wheel velocity. Using a beta, you can find VW2 is equal to minus V2 cos beta. Minus symbol is here negative sign for opposite direction of blade. That's why the velocity will be opposite. Direction is opposite. That's why taken negative here. And this is your minus rho A V into VW1. That is the movement of your water at outlet per second. These are the movement occurring in your turbine when striking of water. After getting striking, it will create a angular movement. This is movement, but it is considering a radial shape and the radial flow is there. That's why it's creating some angular moment here. So using of angular momentum formula, uses what? Angular momentum is your omega into omega. Means mass of water striking, moment of water striking into R1 or omega. That is considered as momentum of your angular momentum. So here is your VW1, R1 is considered as a omega here. So using this omega, you can write rho A V1, VW1, R1. So R1 is your radial distance. This is 0 to R. This is inner radial distance, that is called as R1, which is your rho A V1 and VW1 is your movement of water striking on the vent. After movement of water striking, the angle will be rotated. The angle which is R1 is your angular momentum, the radius. That angular momentum will be multiplied by this, that is a VW1 R1, that is called as angular momentum per second at inlet. Then after we will considering same thing in the outlet, that is a negative sign is there because of opposite direction, minus rho V1 VW2 into R2. This is all about the momentum and angular momentum. Using this angular momentum, we can find the torque. Torque is not nothing but this is the rate of change of angular momentum, that is called as torque. So torque is equal to rate of change of angular momentum. Rate of change of means initial inlet section and outlet section. Difference is your rate of change of. So here is considering the torque is equal to the inlet momentum striking the vane of angular momentum per second at inlet is rho V1 VW1 R1 minus outlet. This is a minus rho V1 VW2 R2, which is called as change in angular momentum, as also called as torque. So using this expression you can write. So this is minus plus and rho V1 is a common for both of this. So we can find the common to both and VW1 R1 plus VW2 R2. This is the expression for torque. So you will find the torque. So you have to find what? For efficiency, so you will find the torque. Then after you will find the work done. Using of torque, the shaft should be rotated. Shaft to against shaft, the torque is created. Means the shaft will be rotated, means doing some work. That torque is equal to what? A angular momentum of change of angular momentum. Work done is equal to what? Torque into perpendicular distance. Or this is the angular distance. Because this is in an angular way, you can consider the angular distance here. So using this work done per second on the wheel, that is your torque into angular momentum, angular displacement. Because angle is creating, that angular displacement is taken as omega. This is omega, which is called as angular displacement. Force into angular displacement, or also called torque into angular displacement. Here is your torque, this is your angular displacement. Using this expression, using this rho V1 VW1 R1 plus VW2 R2 into omega. So omega will multiply in both sides. Consider omega value if you present in radian, that is called as 2 pi n by 60. So u is your pi dn by 60. So when you are considering this R1 and this is your omega into R1, if you consider this, then 2 pi n into R1 by 60. Also you can get 2 R1, the pi dn by 60, pi d1 n by 60. So u is equal to pi dn by 60. So under that you can write inlet blade velocity u1 for omega R1 and inlet outlet velocity u2 for omega into R2, outlet distance. So using this expression you can write this rho V1 VW1 u1 plus VW2 u2. So this is all out of work done per second. So you find up to work done. Now finding efficiency. The efficiency means what? Output by input. So what is your input here? What is your output here? So going through this, first of all you find that the work done per second you find the wheel for your beta angle using a beta below 90. This is a 90, 0 to 90. On that case, you can write rho A V1 BW1 U1 plus BW2 U2. When angle of beta is greater than 90 and less than 180, that is called as obtuse angle. On that obtuse angle, you can write negative sign with BW1 U1 minus BW2 U2. Using this both, you can write the expression rho A V1 BW1 U1 plus or minus BW2 U2. This is all what you have worked done per second in your radial flow type turbine. Inward radial flow turbine. So using this work done per second with unit weight of water. What amount of water will be going through? Input is your work done per second with water striking. When the work done will occur in a shaft, this is your output and the weight is your input, water weight. So using this, you can write rho Q, which is Q is also called as discharge. Discharge is equal to area into velocity. So if you consider A V1, this is also called as discharge. So using this expression, you can write direct input of your rho Q. So rho Q BW1 U1 plus or minus BW2 U2, and the what weight is your mg, which is considered as mg. M means what? Mass. So mass is also rho AB. Using this expression, you can write rho Qg. So using this both, you can cancel with rho Q, and you will find half BW1 plus or minus BW2 U2, which is called as work done per second per unit weight. The value. So using this unit weight, you can find the efficiency, which is called as height link efficiency here. So efficiency is nothing but output by input. In your height link efficiency, hydraulic energy will be occur here. The hydraulic energy is input and runner power is your output. So same principle is given here. This is your runner power. So hydraulic efficiency is equal to also you can write runner power by water power. So this is the formula of runner power is your W by 1000. 1000 is for kilowatt. So W by 1000 into G BW1 U1 plus or minus BW2 U2 using this expression. And water power is your rho G QH. Using this rho G QH, you can write W into H by 1000. So rho G is also called as W. Rho G Q is H is there. So rho G is also called as W. That is just specific gravity. Using this, you can write W into H by 1000. So this is your runner power by water power, which is called hydraulic efficiency. Using this equation, you can find where is W is your common for both. You can cancel with W with W. And 1000 below is there, so 1000 is 1000, and here is a present denominator is a GH, and upper is a BW1 U1 plus or minus BW2 U2. This is your hydraulic efficiency of your inward radial flow reaction turbine. So this is all of the efficiency. Similarly, you can find the mechanical efficiency, volumetric efficiency. So in this way, you can solve the inward radial flow reaction turbine. So that was only. Next video we can discuss further.